Good evening. Oh, we are live. I couldn't hear myself for a second.
Yeah.
Sorry, we're having some technical difficulties this evening, ladies and gentlemen, but if you bear with us, we will be starting. So, good evening and welcome back to the AstroCast Live. I am Joseph C's, your host, and
This is Matthew Barrera.
also your host, the producer of the show. Anyway, welcome back to this iteration of the AstroCast Live. We are going to be talking tonight about the quantum theory or quantum mechanics. It's known by a few names. Leave in the comments. Who do you like more, Albert Einstein or Niels Bohr? And feel free to have a discussion and arguments about that in the comments. But you were going to say something.
We're starting off slow with just a basic topic of quantum mechanics. Nothing to be scared about. Joe's a expert in this field. Definitely. There's no sarcasm in my voice.
No sarcasm at all.
We know very little, but so does everybody else.
Well, there's definitely people who know way more than we do. But, we're amateurs. We like to talk about this kind of stuff. So, before we get into it, however, that's your cue, Matthew. Make sure to hit the subscribe button so you don't miss another episode of the AstroCast Live. We are here live Mondays at 8 p.m. every week, and the clips, if we ever do any clips, and the podcast goes out on Fridays at 5 p.m. on everywhere you can find your podcasts. And you can find me on Instagram at joe.czall, and I think that's just about everything I have to plug. So without further ado, Matthew, I have a question for you. Like normal with this season.
I'm all ears.
Okay. You know what quantum entanglement is, right?
Give me a rundown one more time.
Okay. So quantum entanglement. So, let's give you a little background. Let's say there's a particle. And let's say there's another particle, right? You have two particles. These two particles, we're going to call them entangled.
Okay.
Now, that means that whatever the spin on one of them is, the spin on the other one is opposite.
Oh.
Now, a particle can have two states, spin up or spin down, in this theoretical example. Now, so for example, if our first particle is spin up, then the next particle would be spin down. And the crazy thing about this is it's no matter the distance, it's always it always changes the spin. So for those of you who don't know, quantum mechanics is really complicated. And so the reason this is revolutionary is because we don't know the spin on either particle until one of them is measured. And if we observe and measure one of them, the other one just spontaneously changes to the opposite of what the first one is.
Isn't it where one particle is like one side of the universe and one particle...
It could be anywhere.
Would that information transfer at the speed of light?
So this is really interesting because there's actually no information being sent because it's completely a statistical phenomena. You don't know if the first particle, you don't know what the spin is going to be, and you can't make it a certain spin, or at least not to my knowledge. So basically, this first entangled particle, you just measure it, and whatever it is what it is. And so you're not actually transferring any meaningful information. And it does not travel at the speed of light. It is instantaneous. As far as we can tell, it's instantaneous, which this is what Einstein got into, and this is why I called the episode this spooky action at a distance. And this was Einstein's way of saying, I don't know what's going on. They don't know what's going on. It's spooky.
Wasn't there a test or a theory where you have a box and supposedly there's a cat in it?
Schrodinger's cat.
There we go. Joe, can you explain that to me? Because I do not understand that.
So let's get a little bit morbid, Matthew. Let's say we put a cat in a box.
Okay.
This box is completely hermetically sealed, meaning nothing can get in or out. Now, inside this box with the cat, there is a 50 megaton bomb. Now, this bomb is triggered if you have a radioactive element, let's say uranium. It has a 50-50 chance of decaying. And if it does decay, it sets off the bomb. If it does not decay, it does not set off the bomb. And until this system is observed, it is in a superposition state of being both decayed and not decayed because you have not observed it yet. So then that transfers to the rest of the system. So going on down to the bomb is both exploded and not exploded. That's a technical term, by the way.
You sure?
Oh, yeah, definitely. Then going to the cat. The cat is both in the state of dead and alive. And this is the whole idea behind Schrodinger's cat. And it's a little bit morbid. And you have no way of knowing if the cat is alive or dead until you observe the state of the cat.
Mm-hmm.
And that's the whole idea behind superposition.
Oh, wow.
Are you making me less white?
Yeah, just a little
Am I like super white? Oh, I am like super white.
Yeah, just a little bit.
Just a little bit. Yeah, we ran into so a little bit of background why we're having technical difficulties. I was late picking up Matthew today.
Mm-hmm.
It was the first thing because I had to get gas. The second thing is we tried to set up a green screen, which was supposed to be behind me, but
It looks so good.
it didn't look so good. We didn't have the settings down. We didn't have enough time to get it implemented, and that's why we were late. And so we didn't have time to do a mic check. We didn't have time to. I almost forgot to change the thumbnail on YouTube, so we're a little bit cattywampus. And so
behind schedule.
What?
Little behind schedule,
behind
but we were trying to improve the podcast.
Yeah.
And wait till you have backgrounds. It's gonna look cool.
We'll have the green screen set up next time, and we'll probably fingers crossed. But I digress. That was Schrodinger's cat. I was talking about quantum entanglement, though.
Yeah.
So I had a question for you. Have you heard of an experiment that was teleporting photons with quantum entanglement?
I heard of one where a photon was able to go through a wall.
That's
or a
quantum
solid tunneling.
Yeah, that's different.
My bad, Joe. Joe, can you explain to me the teleportation?
So this was
Go
This was a really interesting concept, and actually it was, I believe it was done experimentally, where they took a photon and an entangled particle, and then they did something with the entangled particle to the photon, and then the other entangled particle basically had another photon that, here, you look it up, I'm not going to explain it well, but basically the whole idea is they technically teleported a photon across using entangled particles. So the thing that I want to know is, with entangled particles, if once you measure it, the other one changes. I think the way it works is if you change this one, the other one instantly changes too. But I could be wrong.
Do you want me to read the official definition?
Yes.
Quantum teleportation involves two distant entangled particles, like you said, in which the state of a third particle instantly teleports its state to the two entangled particles. So is there a third?
Yeah.
This was July 6, 2020. That's a photon. Okay, my bad.
I think that's
Last year, scientists confirmed that information could be passed between photons on computer chips. Even okay, we're not physically.
That's the one I was reading about. Yeah. So read that one. Is there an article?
Yes.
Oh yeah. Let's read that one.
So, yeah, information can be passed between photons on computer chips even when the photons were not physically linked. Imagine the possibilities that opens up now. Okay.
Instantaneous travel of information.
Exactly.
That's so crazy because that.
sorry.
Oh, you're good. That's so crazy because that completely contradicts Einstein's special theory of relativity, and I think general theory of relativity, or maybe just special.
Wrong.
Well, it's possible, but general. I think that might not work with E equals mc squared, because the speed of transportation is infinite. Oh, you read it.
I was just reading the article, and it says quantum teleportation is a demonstration of what Albert Einstein famously called spooky action at a distance.
Yep.
That's where
You want to read the whole article?
Yeah, also known as quantum entanglement. And entanglement, one of the basic concepts of quantum physics. Basic.
Oh yes.
It's one of the basic things. If you don't understand it, then I don't know what you're doing. So,
But of course.
yeah. The properties of one particle affect the properties of another, even when the particles are separated by a large distance. And by large distance, we mean
infinitely vast distance. Yeah.
Exactly.
Yeah.
So this was.
It's hard to wrap your brain around because it's not something you can tangibly see. It's minuscule sized particles. I mean, you can't even imagine a photon. It's so freaking tiny.
When I was little, I always thought in my head, why can't we just have a big long stick that crosses the entire universe and I move it, right? And then on the other side, someone's like, oh, wow, that means A. It landed on A. B. Oh, he's trying to say this. But then someone said, wait a second. When you move one, it's kind of like a...
Here, I'll tell you exactly why.
Go ahead.
So, let's say... Here, do I have a stick? I need a stick. Matthew, there's... Yeah, perfect. Okay. Let's say you have this stick floating in space. Let's say it is... Well, let's start with this pen. If I push this end of it that way, the other end is going to go that way. Because it is so small comparatively to the size of the universe. Now, if I were to put this in a hydraulic press, what do you think would happen? If I put it end on end in a hydraulic press, it would compress. So what you don't see when you push on this is that when I push on this, the molecules in here are then pushing on each other in that way, in that direction. And it's almost instantaneous that the other end moves. Sorry. Yeah. It's almost instantaneous that the other end moves because it is such a short distance. Now, if you have, let's say, a 4 light year long pen like this, if you pushed one end, it would take that compression wave so long to reach the other end that it doesn't break the speed of light.
It doesn't.
My little mind was like, oh, that's just a simple solution. Why hasn't anybody thought about it?
Yep. People have.
People
have.
I'm looking at more articles for you.
Okay. So when I first learned about quantum theory, it's actually, you know what I learned first before I learned quantum theory?
What?
String theory. Now, string theory, if you thought quantum theory was crazy, string theory is even crazier. It's saying that everything's defined by 11 dimensions and everything is basically made up of strings that wobble at different frequencies, and the different frequency creates different energy levels and and that basically explains the entire universe. At least that's the theory. Go for it.
There's an article by Futurism. I don't even know if it's fake or not, but it had a very catchy title. It says, scientists just teleported a photon from Earth to orbit for the first time.
Oh, yeah, that was real.
That was real? Okay.
Yeah,
it says, this is an essential step towards establishing a global scale quantum internet. Can we talk about that, Joe?
Whoa, I've never heard that before. That sounds pretty cool. That would be instantaneous travel.
Yeah, you did
information.
Say that. Yeah,
instantaneous travel of information.
Mm-hmm. So that's really interesting, and I really want to know why that doesn't break Einstein's special relativity. Because, I mean, it sounds like, I mean, you know, I don't know everything, obviously, but it sounds like to me it breaks Einstein's special relativity. So is Einstein wrong, or are we measuring something wrong? You know, or do we have a fallacy there? The other side of that is, sorry, I cut you off.
Is it hard to accept that maybe Einstein was wrong about something?
Yeah, maybe. I like Einstein. He's a cool dude. Most of what he has predicted and calculated has stood up. Actually, I think everything has stood up thus far that he's done. I don't think there's a single example of his theories breaking other than quantum.
And
can I have an example for the breaking?
Well, information traveling faster than the speed of light. But I think the way they get around that is they say it's not meaningful information. Or it's not controllable information. But I don't know that really... So I don't know. Quantum is weird, and it's just completely different than the macroscopic. And there's completely different forces at play because gravity just is meaningless at the quantum level. And it's just really weird and really interesting.
Can we talk about the video I sent you? I know you've seen all them.
Oh yeah.
All the theories and stuff. It was funny.
My favorite one was quantum healing.
What's that?
It's not existent. It's a fake. It's a scam. people on Amazon will sell like quantum healing, heal your your illnesses with quantum sounds and quantum therapy. It's just buzzwords. It's meaningless. And in the video that you sent me, excuse me, he said quantum healing. This is wrong. Don't. Or he's like just very quickly. It's just like this is BS and moving on. It was kind of funny. I forget how exactly he said it, but no, that was my favorite because that was something I'd never heard about.
I have another. Can I switch this topic just a little bit? Sure. There was a video I saw on YouTube. It's about how in a small town, for Illinois or whatever, they were doing a small mayor election, right? They were counting the.
I think
you think you got it?
No, keep going.
Okay. They were counting the votes. They were first. This is the first year they were using an actual electronic voting machine, but they were also, as a fallacy, using it also doing backup as you're using physical at the same time. And for some reason, one of the candidates gets an extra. It's a very specific number that's important, but I forgot it.
Oh, okay.
It was an extra around 600 votes.
Okay.
And they're like, there's something wrong with the system. So they count everything back because they also had the paper votes, and she had 600 extra. And they were wondering, okay, maybe it's a computer. They looked through the computer. Maybe it's a code. They looked through the code. Maybe it's the hardware. Maybe something happened. They checked everything. Nothing was wrong at all. Do you know where I'm going with this?
Maybe. Okay. This isn't actually the one I was thinking about. But
okay. So I can't remember the video to its precise thing where it was going in depth for 30 minutes about how the motherboard is programmed or how the bits are changed in order to give information to the computer. Well, one specific bit information was changed, and it led scientists to believe that an outside energy or photon hit that bit or whatever, and it changed that number perfectly. And everybody's wondering what happened. How did this happen?
528.
That's the number. 528 around or 26. See, around 600, right?
Yep.
And it was because you want to say it, Joe?
Well, binary.
Binary?
Yeah,
No,
that's why.
the energy came from a distant galaxy exploding, and the energy came from all the way across the entire universe, went to Earth, and it hit that exact bit.
The odds of that, man.
And it
So-
changed the number.
The whole reason that something like that can happen, and it happens probably more than you think, but there's actual hardware and computers that we use to recognize malfunctions like that and to remedy them. So I'm not quite sure why the hardware didn't detect that, because normally things have fail-safes and they have especially over the internet, there's I forget the exact technical term, but it's they figure out the error between because you're always going to have some sort of error between transmitting data, because there's electromagnetic fields everywhere, light is everywhere, and that can just affect your electronics. But the whole reason it's 526, I think that's the number, is because it's binary, and if you change one bit, it changes the number by either 1, 2, 4, 8, 16, 32, 64, 128, 256. Maybe it is 528. I think it is 528.
It's 528.
Yeah. And the whole reason, I'm assuming most of you know how to count in binary and how to do stuff in binary. But essentially, I'm not going to explain it. It's going to take too long. So I'm just assuming everyone knows. And if you don't know, just look up how to count in binary and you'll know what I mean. But basically, if you have enough bits in the computer, usually computers calculate numbers in around the 64-bit range is what computers do nowadays, which means you have 64 different slots that the numbers can set into, and each different slot can hold a 1. You want to take his call? All right, we're gonna take a call live on air we're having someone named Alex calling in to the podcast.
You want to be on live?
What's that?
We're doing the podcast right now. Do you want to talk for the podcast?
No, it's... You reading my comments?
You've been commenting.
Oh, he has been commenting.
Yeah.
We can read some.
Read your chat,
Yeah.
Okay, well, I'm gonna have to hang up, but I'll read your comment.
No. Call him in. Call him in.
Comment?
Yeah.
I will put you on mic. You better not say anything.
What?
We have you on mic.
Oh, you do?
Yes.
I'm a big fan of the show. Long time listener, first time caller.
What's your question?
So are you saying that every time I fuck up in a game, it's because of space magic?
Definitely, yes. Absolutely.
Okay.
100%. Sorry.
Just blame it on like galaxies exploding somewhere else.
You're not bad at Titanfall. You're not bad at Titanfall. It's actually just the aliens playing tricks on you.
Man, I could kick your ass even with the aliens.
We're kicking you off the air.
Yeah.
Bye.
Oh, brother. We do have a few chats if you wanna read some chats.
Yeah, I
We're
got
about
you.
halfway through.
Gotcha.
So these chats are from like 8:15, so they may be
Okay.
irrelevant. But
Let's see. Okay, we're not gonna read the first two. Let's see what. Okay. And okay. Yeah, we're not reading any of those.
Alexander had very good comments,
Yes.
and we keep getting this one comment from this one person. It just simply never makes sense.
No,
Every
vomit
time they
today.
every time they comment,
Yeah.
it's capital letters,
Yep.
and it just like I don't under. It said,
Vom today. I don't know.
and every time I go to the channel, it's recently made, so I don't know if it's a bot.
I'm sure
or it's a
probably
child.
bot or like a scammer or like something. I don't know. It's definitely weird.
It is weird,
Vom
but I'm
today.
I'm glad Scrumpus has 2 accounts commenting for us.
Helps us out.
Get those interactions up.
Yeah.
All right. Well, that was a little bit of a derail. Do you want to? Now who's calling you? Oh my gosh. Okay, don't put him on. Okay, so I guess I'm stalling for time now. Oh no,
No,
you're back.
go.
Okay. Okay. Sorry for the interruption.
Sorry for the interruption.
We were talking. I'm trying to find the video right now of
Oh,
what it
okay.
was talking about, but it may just be. I think it was supernova explosions that affected the binary. It clicked one of the timer. I don't know how it perfectly hit it. It went across everything, time and space, and it hit that. It's just insane.
Well, the chances of that happening, it's very small. But we get bombarded with particles from outer space, from outside of our solar system, galaxy, all the time. Most of them don't affect us because we have a strong electromagnetic field, relatively, around the Earth. And we have the wonderful atmosphere, which soaks up some of them. And then we have, a lot of stuff in between us.
stuff.
And, I mean, it's generally just a lot of things and stuff and matter between... Which some particles, like neutrinos, don't care. They'll go through anything. Neutrons will pretty much go through anything too, which is why they're so dangerous in like gamma particles. I think they're gamma particles, but in radiation in general. But let's see.
That's until we have solar flares, and it just.
Well, solar flares are a different story. Solar flares are dangerous because they're so close to us and they're so high energy.
Do you remember that time where everybody freaked out when all the electronics went down with that one solar flare? I believe it was
I don't remember
2007.
I
Yeah.
don't remember that at all.
Alexander saying, "Put him on." No.
No.
Turns off.
So, I guess I'm stalling for time now.
No.
Oh,
You could talk about
Okay.
the effects of a solar flare on everything on Earth.
so solar flares are just highly magnetized particles, or ionized, or however you want to say it, particles, and they absolutely disrupt everything. It's like a giant EMP blast, like from a nuclear device. And for those of you who don't know, an EMP or an EMP is an electromagnetic pulse, and it's basically just a wave emanating from a source of electromagnetic radiation, which is, you could call it light, you could call it whatever, but it's usually high energy electromagnetic radiation. Now, I'm an electrical engineer, so I'm going to get a little nerdy for a second. The way electricity travels is in electromagnetic fields. When to move electrons through a wire, you have to have an electric field, and a magnetic field is generated because of the movement of electrons. The electric field is always perpendicular to the magnetic field. Now, when you have an electric field, this creates a potential difference. When you have an electric field of some strength here and a smaller strength here, there is a difference between those 2 points. That difference is what we call voltage. When you have a voltage, now you can have a current passing from the high potential to low potential until there is no potential, or the potential is equivalated. That's not a word. Equivalent is the word I was looking for. So when you have an electromagnetic field going through, let's say, electronics, and it is a high enough energy, it will just send a current through everything, destroying most things. And that's because chips operate on very specific voltages and frequencies. And if you exceed those voltages or frequencies, then the chip will quite literally just catch on fire and destroy itself. And this is why EMPs are so dangerous in the modern world, and it's why solar flares are so dangerous in the modern world, is because we rely on the internet and technology and electricity just so much. So when you have an electromagnetic field or radiation just coming through and going through everything, you're creating high voltages and high potential differences that current can then flow through in chips, and you're basically inducing current in electronics.
How big of a solar flare does it have to be, or is it possible for a solar flare?
It could miss us.
It can miss us.
Yeah, it has to hit us first.
Is there a high probability that a solar flare could hit us first of all, and disrupt our internet for a week, and have power outages across the world for a week?
For a week?
Yeah.
Or usually lasts a couple days,
So
right?
it depends how big the flare is. It depends if it's big enough to encompass the entire Earth. If it's big enough to encompass the entire Earth, then we're pretty screwed. If it is just localized, which we have those a lot more frequently than you might think, they just get absorbed by the electromagnetic field. If it's high enough energy and it's just localized, we have a lot of redundancies in place. So this is a really interesting topic. It is really hard to turn off the internet. The internet it's because it's not really centralized. There's no like one internet, it's decentralized between, servers. Your computer, your neighbor's computer, everyone's computer. It's all a server on the internet, or a node, or whatever you would like to call it. Because of the decentralized nature, you could take it out in places, but it'd only be a matter of time before they got it back up and running, or just rerouted it. There's quite a few physical cables that run on the seafloor connecting North America, or connecting the Americas to Afro-Eurasia. There's actual physical cables under the sea. And this is actually, so I won't go on a tangent from this tangent.
Let's go on a tangent.
But, if you want to go on a tangent from this tangent, when they were originally laying the wires for telegraphs from the Americas to Europe, or from North America to Europe, they encased the wire. Well, so let's give it a little background. If you have a wire and you have a voltage on either end and there's a current going through it, which is the purpose of a wire pretty much, there is going to be generated a magnetic field. This magnetic field, if it is, let's just keep it simple. I keep saying electromagnetic. The magnetic field can induce a current in, let's say, anything that's ferromagnetic, meaning anything that has iron in it, or any kind of conductive metal like copper, or anything that conducts electricity can have an induced current into it. So they have these telegraph wires, which are just wires that have a voltage on either end and a current going through them from the high potential to the low potential, and that current creates a magnetic field. That magnetic field can then induce a current in something else. So this telegraph wire that they laid on the bottom of the Atlantic Ocean, they first encased it. Do you know what they encased it in, Matthew?
What?
They encased it in steel. So the wire that was going through then induced a current in the steel surrounding it. Then the steel surrounding it, since now that had when you induce a current into something, it creates a voltage pretty much. Then now that you have a current going through there, that current then produces another electromagnetic field back on the original wire. So this basically made any kind of telegraph communication from North America to Europe impossible with that wire because it was completely encased in steel.
Yeah.
And so that was a tangent I didn't mean to go on, but
No, it's fine.
we fixed that problem with the internet cables on the bottom of the seafloor because we use polyurethane on the outside of them. So
How does that?
polyurethane is plastic.
Oh, plastic.
It is not made of metal, and therefore you can't induce a current into it.
I didn't know that was plastic.
Yes.
I'm sorry.
Pretty much anything with urethane or poly is plastic,
I should.
or some kind of man-made molecule or some sort of oil-based, petroleum-based chamanama. So. Aurora borealis. So that's ionized particles from the sun hitting the Earth's magnetic field and being channeled all the way to the North Pole and the South Pole. And so, I mean, you're literally just, seeing solar flares being brought down to the surface. That's the only spot, if they hit the magnetic field and they're picked up by the magnetic field, that's the only two spots on Earth that they'll actually hit if they're not of significant energy. So, I'm actually not real sure why they reverse, or how. I should say I know why they reverse. I should say I don't know how. But we have seen through geology and archaeology that there's certain sediment layers where we can see that the orientation of the particles is different to the orientation of the other particles, and these particles are ferromagnetic. And this is caused, in theory, by the switching of the poles. So let's say if the North Pole's on top, the South Pole's on bottom, then the particles are going to be orientated to the magnetic field, like, let's say like this. Or, let's just say up.
I have an explanation.
Oh, go for it. Render them useless. You just have to use them backwards.
Yeah, just use it backwards.
That would not be a big deal. You'd just see some birds flying the wrong direction in the winter.
And they'll die.
Yeah. Which kind of isn't really funny, but it kind of is. But anyway, yeah, that wouldn't be a problem. You'd literally just be able to say, okay, do everything the opposite.
Oh, that's funny.
What? Oh, yeah, so the whole reason that we have a magnetic field in the first place, or at least the theory, because no one's been to the center of the Earth, obviously, because it's really far down there, and it's kind of hot. Your mic is off.
Yeah, Scrum just pointed out to me. I couldn't hear myself either.
Oh,
Go, keep going.
that's not good. Well, you can fix it. So, don't put him on again.
I got it. Tell him I got it.
Okay, he got it. So the whole reason we have a magnetic field is because we have, or at least in theory, a liquid, mostly iron, outer core of the Earth. The inner core is mostly solid because of the pressure, even though it's really hot. So the outer core is liquid, and the reason we know this is because of something called P waves and S waves, waves that are generated during earthquakes, and the S waves can't pass through liquids. The P waves can pass through liquids. And we noticed that the P waves could pass through the center of the Earth, but the S waves could not if you had an observer on the other side and there was an earthquake on the opposite side. So that's the short reason of why we know that there's a liquid core.
That's something.
What? Oh.
Why? I never clicked it. There we go. It's working for some reason.
Yeah, okay.
To reiterate what I was saying before I was
Yep.
cut off, I was just saying how genetic mutations could be caused by the added stress to animals when there's harmful ultraviolet lights from the sun that come in. And it also says an increase of particles from the sun entering Earth's atmosphere could also cause disruption to satellites, other communications,
Yep.
of course.
Yep. That's what we were talking about earlier.
Yeah.
But yeah, basically, since it's a liquid core, the molecules are in motion a lot more than if they were to be solid. And so, well, the whole reason that we have a magnetic field in the first place is because they're in motion. If the particles were stationary, we would have a significantly less energetic magnetic field. Because the Earth is technically like a magnet, but the whole thing with magnetic fields, and you kind of have to get into something called Maxwell's equations with this, but generally speaking, if you have a current passing through something, it doesn't generate a magnetic field automatically. It has to be in motion to generate a magnetic field. So either you can have a current that generates a magnetic field, or to generate a current, you have to move a magnetic field. So it's kind of inversely proportional in that sense. But what's up?
What are exotic particles?
Oh, I have no idea. I'm just going to say that. I have no idea. I've
reading
heard
this.
that term thrown around a lot recently. I have a feeling it's just something we don't know yet. But
Buzzword.
what does it say?
Strongest ever magnetic field fails to make predicted exotic fields. Researchers have used the strongest magnetic field ever to measure the search for exotic particles called magnetic monopoles?
Monopoles.
Monopoles.
So
They
magnetic
came up empty.
monopoles. That's a really interesting concept because magnetism is always exists in dipoles, and that's the whole reason that there is magnetism based on Maxwell's equations. So think of a magnet. You have a north and a south. Think of the Earth. You have a north and a south. There is no magnet that just has one north. If you cut a magnet directly in half between the north and the south, you'll create two magnets that each have a north and a south. So that's a really interesting concept, and I have not heard of a magnetic monopole. That's crazy. So that probably gets into quantum mechanics a lot. That probably brings it right back to quantum mechanics, because there's actually a class at the university I go to that covers quantum mechanics and calculating a monopole theoretically to calculate the dipole in a permanent magnet, which is really complicated, and it's so that you don't have to use Biot-Savart. But anyway.
Is that the highest?
No.
It says the magnetic field is why did it say 2 billion times stronger? Is that a typo?
No, you could just.
I guess
That's just being lazy and not using scientific notation.
Oh, okay.
It says they're not giving up yet though, so they increase it, I guess.
See, that's something. I don't know that that's going to be possible to create a magnetic monopole.
It also says here.
Some models of the universe predict that there should be particles with only a north or south pole called magnetic monopoles, blah, blah, blah. Oh, I thought they were going to say that they're multiple. We'll explain. Oh, the existence of magnetic monopoles would explain why electric charge is quantized. Quantized, I'm sorry. Meaning it would come in packets of minimum size.
So electric charge is quantized like that. That's what electrons are.
Oh, okay.
It's
just reiterating.
the minimum amount of charge, yes. Keep going.
Okay.
So over the past century or so, researchers have searched for a magnetic pole both in space and the smash-ups of particles at colliders, but they haven't been found yet. Igor Ostrovsky, I can't say this name. Ostrovsky.
Let me see.
Tell me how to pronounce this, Joe.
Let's see here. Where? Igor Ostrovsky.
Ostrovsky.
Yeah, Igor.
And he's from
Ostrovsky.
Alabama.
Oh! That's a little funny.
He looked for monopoles being produced by a proposed phenomenon called the Schringer Effect. Wherein,
Schringer Effect?
yeah, extremely powerful magnetic fields
Schringer
could
Effect?
spontaneously produce magnetic fields and their antiparticles.
Spontaneously produce magnetic fields.
Wow.
Huh? That's interesting. How do they say they're doing that?
It just says they're doing it.
Oh,
So
okay. Well-
magic.
Yeah, that's interesting.
See,
Joe, any science we don't understand, it's magic.
Yeah, pretty much. That's the whole premise of like all the Thor movies, isn't it? But that's a tangent we don't need to go on.
Yes, you do.
No, we do not. It's already 8:46, so we've only got 15 minutes left. We've pretty much gone on a long tangent away from quantum mechanics and gone all the way back to quantum mechanics.
Well, everything's connected, Joe.
Oh, everything's connected. You want to talk about the what's on the whiteboard?
You're the most qualified to say that.
Oh my gosh.
So Joe has something on the whiteboard.
So I think I'm onto something, Matthew. I think
Joe is crazy.
I'm definitely crazy.
He's insane. He needs to be put on his pills. But before we do that, we need to hear him out because maybe he has a point to give.
So I've been doing a thought experiment recently, and it's basically this premise: what if you could model everything off of one equation? And I've been calling this the ultimate definition. And let's call this ultimate definition Z because it's the ultimate letter in the alphabet. How creative am I?
So creative.
Yeah, woohoo. So let's call this ultimate definition Z. So now, if we think about dimensions in space, like what are we made of? We're in three-dimensional space, so we have 3 dimensions. But what happens if we move in dimensions? Well, then we have time. So what time is... Well, now you're in the 4th dimension. Then in the 4th dimension, then now you have time in the 4th dimension. You create the 5th dimension. So my whole theory, and it's kind of similar to the string theory in the sense that it talks about dimensions, but that's pretty much it. If you can define everything by its dimensions, then that's its ultimate definition. So along this line, if you... Let's call its dimensions S. So Z would be the integral of S, meaning the sum of all of its dimensions. And let's say S to the power of n, n being some dimension, would be our function. Now, if we think about that, if you have S to the 1, then if you move to the S to the 2, that is going from the 1st dimension to the 2nd dimension. To go from the 1st dimension to the 2nd dimension, you multiply by S to get from S1 to S to the power of 2. And that's just algebra right there. But now if you think about it, to go from the 1st dimension physically to the 2nd dimension, you move something with respect to time. So you're technically also dividing by time. So I make the equivalency that S to the power of n is equivalent to 1 over t to the power of n, t being time, n being the number of dimension. Now, this is where it gets interesting.
Can I interject?
You can.
If Joe ever taught a class, half the class would be too scared to raise their hand and say, Mr. C's, can you say that for the 5th time again?
Yeah. Well, you know, it makes sense to me, and I'm trying to explain it well.
And that's the problem.
Yeah. So you can feel free to call me crazy in the comments, but so this is where it gets really interesting. We can say, let's say we have S to the power of 4, meaning the 4th dimension. We could also express that as S to the power of 3 divided by time, which means S to the power of 3 over t to the power of 1. For example, we could also say if we want to, let's say we're in the 2nd dimension and we move time twice, that's still in the 4th dimension, so S to the power of 2 over t to the power of 2. So we get this other function here, and we're going to call this S to the power of alpha 0 over t to the power of alpha 1, where n is equal to alpha 0 plus alpha 1. And this basically means that the total dimension may not exceed alpha 0 plus alpha 1. And this essentially is what we just explained, that if you have, let's say, the 4th dimension, you could express it as S to the power of 3 over t to the power of 1, S to the power of 4, S to the power of 2 over t to the power of 2, and so on and so forth, because S to the power of n is equal to 1 over t to the power of n. So now let's substitute this back into our original ultimate definition equation. You get z is equal to the integral from negative infinity to infinity, by the way, of s to the power of alpha 0 over t to the power of alpha 1, where n is equal to alpha 0 plus alpha 1. Then we get into something called hidden numbers, or at least that's what I'm calling them, because when you make a table of this and you try to move from dimensional shell to dimensional shell, and this is basically saying if you're in the 4th dimension, you can express that as s to the 3 over t to the 1, or s to the 2 over t to the 2. And those are all each different shells. And so if you want to go from s to the 4 to s to the 3 over t over 1, then you need to move dimensional shell. And you're going to the right, I guess you could say. So now if you continue that and you keep going less in the s power and more in the t power, you eventually get to 1 over t to the power of 4, because that's also equal to s to the power of 4.
I blanked. Okay, so I had to do something, right? I was hearing Joe, right? I had to do something real quick, and then I came back into reality, and then Joe was talking, right? And I was like, oh, I should never have left him for 4 seconds. The train has sped. This train has sped off beyond the horizon.
Well, we've only got 10 minutes.
And I haven't ran back. I can't run back to the train.
Oh, I'm sorry, Matthew.
Okay.
I'm sorry to our viewers. You probably have no idea what I'm talking about.
Just rewatch
But
it lots of times.
yeah, you can rewatch it 5 times. So you get to this thing where eventually, if you start from the t side and you start from the s side, if you have s to the 4, well, so we agreed that s to the power of n is equal to 1 over t to the power of n. That's my hypothesis, and that's what I'm saying. I already told you that was true. So just take my word for it. So that means you can express s to the 4 as 1 over t to the 4, or you could say s to the power of 2 over t to the power of 2. That makes sense, right?
Yes.
So anyway,
I look insane.
if you start from the t side and go towards s, and then if you start from the s side and go towards t, eventually you will get to a spot where the top is equal to 0 and the bottom is equal to some, the top is equal to 1 and the bottom is equal to either t to the n, or the top is equal to s to the n and the bottom is equal to 1. Now, this just so happens that it meets in the middle, and both of them disagree on what should be there. So that's what I call a hidden number, and I call that h.
Josh said there's too many dimensions.
Yes, if maybe.
And
This
he
is
said
a
if
theory.
you want more dimensions, just find a tesseract.
Okay. Marvel fan down there. So the tesseract. Well, I'm not gonna go on that tangent. I'm not gonna go on. That
Go on the tangent of tesseract.
So eventually we get to this other number k that I define, and then you have to multiply everything by k. But eventually we get to the definition that the ultimate definition of something, z, is equal to the integral from infinity to negative infinity of s to the power of alpha 0 divided by t to the power of alpha 1 times everything times k to the power of beta, where beta is the dimensional shell. So this is my whole theory. I think I'm onto something. I think I'm probably about 75 to maybe 98% wrong. So I need to work through that, but
But there's a hint of truth.
I think I'm onto something. Because the way I did it, and I've been working at this for a while, and I pretty much just started over the other day on this, and the way I started doing it just clicks into a lot of things. Like I was able to, the other day, just completely from scratch, using this, just develop derivatives and integrals just from the ground up from this equation.
So,
And then I was also able to just create imaginary numbers using this equation, and I was able to. I haven't done irrational numbers, but those are still real numbers. So I'm pretty certain I can still make irrational numbers because they're real numbers and not imaginary. But anyway, I think I'm onto something because everything's kind of clicking in place very nicely. But it could be a coincidence.
You get to that point where scientists have the theory down, and then something so far away from
Yeah,
the
it just
subject comes in
changes
and completely derails it, disproves it, and says, nope,
Yep.
this is the way. And I was like, oh,
Yep.
well, that was all for nothing.
Yep. And my original jab at this was interesting, but it kind of ended up like that, where it was, well, where am I going with this? It doesn't really explain anything. It's a cool graph. It looks cool, but it doesn't
Not
really
enough.
explain anything, you know? So that's kind of where I ended up last time, but I think I'm onto something this time. But anyway, enough of babbling about me. Do we have any more chats? No, we don't have any more chats.
No.
I have a question for Joe.
Okay.
What's the meaning of life?
42.
Perfect. That's
Yes.
the exact answer I wanted.
No, the meaning of life is what you make it.
what you make of it.
What if I
Or-
make nothing from it?
Well, then that's your meaning.
My meaning is nothing?
Yep.
Sick.
Yeah. No, honestly, the meaning, or at least the meaning that I've found, and we'll end on this.
Okay.
It is to be. No, sorry. To will the good of the other, for the good of the other, and to desire to be in relationship with the other. And that basically means love one another, because life's too short to have hate fill your heart.
Yeah. Well, you know what mine is?
What's that?
Use your time very wisely because it's so limited. It connects to yours. Just use it well and don't regret the things you do.
Mm-hmm.
That's it.
Well, on that note, thank you so much for watching and tuning in tonight. We will see you back here in exactly a week, minus 1 hour. And you can follow us on Instagram at joe.czal. You can find us anywhere you listen to your podcasts, including Spotify, Apple Podcasts, Google Podcasts, Overcast, Anchor FM, and pretty much anywhere you find your podcast. Subscribe to the channel if you're interested in our content and you find yourself coming back here every week. And hit the notification bell so you do not miss another episode of the AstroCast Live.
We can end it on one more comment.
And we will end on one last comment.
So,
Joshua Bropp says, think of it like this. Your theory could teach you things about the real world even though it's not totally what you want. Sort of like how building a small wooden boat can teach you something about building a cruise ship.
Joe, take from what we all with that.
There's a certain wisdom in that.
I like that.
Yeah.
Thank you, Josh.
So we're going to end on that note.